before I do that, let me just say for anybody who's new, my name's Mark Martin and I'm the VP of programming for the club. I organize all the meetings and so forth. Um, so if you're new to the club, welcome. And now I'll turn it over to our president, Margaret McRae.
Hi, this is the business portion of the meeting, and this month it is going to be very short. Don't have a lot to share with you, but we have something. I'm going to try what I have not done in the past, but here we go. Welcome to June 21st, 2021, and happy solstice. And the video works. I'm pleased. Let's see. Our membership is holding pretty steady. This is why I like to do this in edit view rather than this way. Okay, our membership is at 725, and a year ago it was 730, and 2 years ago it was 741. So we're holding pretty steady. I'm not too worried about this. Our telescope workshop is on Saturday, June 26th, and it is online. You'll get a link in your email. Watch your spam folder or your promotions folder that Gmail has, or whatever your email system has, for shunting emails that they think are, trying to sell you something, or political advertising or something, for notifications from RCA. Because a lot of people, we send out emails and then they tell us they didn't get it. So be sure to check your spam folder. The Astro Imaging SIG is going to be on Tuesday, July 6th. We're still doing Thursday night dinners with RCA on Zoom and Friday lunch with RCA on Zoom. It looks like the governor is going to change the guidelines for meeting in person at restaurants, probably at the end of this month. So I will call McMenamins about a week before our next projected RCA Downtowners lunch on Friday. And if we get a thumbs up and we can schedule this and reserve it, I will send out a notice and I will put it on the forum also. Our next meeting is Monday, July 19th. We are having an RCA Club Star Party, our first one in, I don't know, 2.5 years, something like that. What's September of 2019 or October of 2019. July 9th to 11th at the White River Snow Park on Highway 35. It's free. You do not have to register. These Club Star parties are different from the big OMSI Star parties, which are free and open to the public. These are really almost elaborate camping events. So do come with enough to keep you going. You need warm clothes, you need something to sleep in, and we are renting a porta potty to have there on the premises. And bring any observing gear that you have. If you are a new member and you don't have a telescope yet, that's fine. If you have a pair of binoculars, bring that. If you don't even have that, just come and learn what you can. We'll be, people are willing to help you out. We're going to ask you to mask yourself when you approach someone else. If you're standing, kind of walk up to somebody, you should have a mask on. White River Snow Park is big enough, it's huge, that we can set up far apart from each other. And that, as far as I know, are the only principles that we have to follow regarding COVID. I did send out via our email system a 2-page description of how we're going to handle the next 6 months, or what we're foreseeing for the next 6 months. Please check your spam folder, check your RCA filter, check for your, search for RCA messages. I also put it on the forum. and I'm announcing it here. So please go look for it. I didn't want to put it in here. It's too long. So check it out. We have a lot coming up. And that's it. That's all I have for this month. My business meeting was very short this month. I'm going to turn it back over to Mark and Jim.
Great, thanks a lot, Margaret. Now we'll have our monthly sky and space report from Jim Todd. Welcome, Jim.
There we go. Hello, everybody. Hope you're staying cool and definitely observing time. And lots of things are happening in the month of May and June. So since the last meeting, a couple of eclipses, and starting with May 22nd. And they did the first testing of the Spaceship Two from the New Mexico, what do you call it, landing airport. And so it was a successful launch, and it went up to, I believe, 60 miles, 65 miles. And so it launched and had a successful landing. And then we had, of course, the moon in the full moon in May was a flower moon. And but what's particular about that particular full moon, it was a total lunar eclipse. It was also called the supermoon and the blood moon, the flower moon, you name it. And so had a variety of names, and that particular eclipse was fairly low. And so there've been some good pictures. This particular picture was taken by Mike McKay. And so shot from his location. It's a nice picture there, nice clear skies, very nice angle for the eclipse. I was able to see it a little bit, but mine was quickly lost in the trees. Didn't get a good angle on it, but nice picture by Mike, that's for sure. Right?
Beyond the increases I have earlier requested for space activities, to provide the funds which are needed to meet the following national goals. First, I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth.
That's 16 years ago. There was John F. Kennedy that made a commitment to sending man to the moon. It's hard to believe, 60 years ago. I actually have a few kids that coming up to me and say, do you remember that, Jim, seeing that announcement? I said, no, don't go there. Okay. And then on the 28th, they came out with this picture, it's believed to be one of the oldest or furthest distant galaxy, somewhere in the neighborhood of about 13 billion years ago. Million light years. And so Buddy, yeah, what do you expect? So this came out on the 28th. And then the ingenuity continues to that they prevail, but on the sixth flight had a lot of hiccup. And so you know, there's a lot of confidence in this ingenuity, but this one in particular had a little bit of a wobble. I'd never really seen anything that came out saying why, but it was oscillating a little bit, but it recovered and it was successful landing in a new airfield. So now ingenuity is going to kind of go along with perseverance, which many people are happy with the idea, actually, but had a little hiccup. But what's interesting, though, after that flight, is that they're seeing there's a lot of dust on the solar panel on top of the blades of ingenuity, if that's anything to do with it. Then Juno came out with a beautiful picture of a close flyby of Ganymede. And so this is a really nice resolution and details of the surface of Ganymede. There's more to come, but this is just a teaser showing great details of the largest moon in the solar system. And then Ingenuity did it again. It went on the seventh flight, no problem. And my understanding yesterday was the eighth flight ingenuity, and I haven't quite seen anything yet. But it's moving along, perseverance and ingenuity. But you think about it, it's been there for 116 soul days. You think, wow, it's been there for a long time. But funny thing is, it's only gone half a mile, right, from the landing site. But it's making a lot of progress. And then on June 10th, we had the annular eclipse, which occurred on the new moon. So we had a full moon with the lunar eclipse. Now we have a new moon with the annular eclipse. And there was quite a bit of streaming that was going on that particular morning. This is a view from Canada. And there's another one at various spots around Canada. So folks over there got to see the annular eclipse occurring on June 10th. This is going to be kind of a precursor for us in 2023. In October 14th, I think is the date, that we're going to see an annular eclipse going across Southern Oregon. I know Wes is pretty excited about that, but there's going to be a great opportunity for Oregonians to see their very own annular eclipse in 2023. And then, so many of you saw this shot here from the China rover. What a snapshot. It was taken like a little camera box. It was dropping them, and they were designed to take a picture. It looked like, kind of remind you of the little Brownie camera. Okay? And so they got some nice pictures out of that. So nice and clear. Then on the 13th, Hubble, it's been put on the safe mode. And so, you know, you should think about it. Well, they got the 1980s computer. And there's been a lot of joke that, well, it probably needs a window update. Who knows? But it's on the safe mode, and I haven't heard anything that had been recovered or not. But let's just hope that Hubble will be able to reboot that 1980 computers without much of a problem. And then on the June 17th, China sent 3 astronauts to their very own space station. Successful launch. It only took them 6 hours to go from launch and making a docking with the space station. So they had a very successful mission so far with their very own space station. I tried to look for it not too long ago in the night sky, but I couldn't see it. I had a lot of high clouds overhead. And then, of course, we just passed the summer solstice just yesterday. A lot of calendars say it's today, June 21st, but it's universal time. But if you put it into a time zone, it puts it back on the 20th at 8:32 p.m. I know a lot of people are pretty happy about the first day of summer. And so we have, of course, 16 hours of daylight, and making it the longest day of the year. And I think that's probably why Jan is heading to the beach, so she can enjoy some of that sunshine and what have you. But it went over the Tropic of Cancer, and we have 16 hours. So after June 23rd, the days would gradually start getting shorter until we get to the winter solstice in December. And so up in the Arctic Circle, it's the midnight sun, and it's 24 hours of daylight. It's one of those things I'd be kind of curious to see someday. I wanted to see what it'd be like to be up there for 24 hours of sunlight and also be continuous sunrise and sunset. I think it would be quite fascinating to be up there someday. And then the not diluted clouds are starting to appear. They're also called the nightshade clouds. This one's taken by somebody in Enterprise, and they're starting to appear. There's actually an alert going out right now. So who knows, maybe after this meeting tonight, those of you can go out and maybe see the not diluted clouds. What they are, it's just something, I'll talk about that in just a minute, something that's fairly high up in the upper atmosphere. And here's one that's taken by Roseburg. This is I mean, if you see it in Roseburg, this definitely should be a potential that you can see it here. This is now the time that we can start seeing these events during when it's warm here in the Northern Hemisphere. It'll go on through most of the summer, but apparently there's an alert being put out for the non-diluted clouds that are going to be visible. Sunspots, done it very active still. Kind of taking a nap at the moment, but there's a lot of activities. So clearly seeing that we're entering the cycle 25, the sun cycle. And there's a very large sunspot on the upper right of the sun right now, right? But looking ahead, as I mentioned, the non-diluted clouds is now what they say is very active in the Northern Hemisphere. And so what it is that it's the clouds, it's way up in the upper atmosphere. And from the angle that we're looking at, it's the sun that's reflecting off these ice particles and what's called meteor dust, and reflecting off these clouds. And then from our view, with the sun below the horizon, that we're able to see these clouds. I've seen them a few times. They really are quite spectacular. They're really beautiful. So check it out afterwards, right? Planets is pretty much where we see right now in the evening. We have Venus, it's really bright, -4. Go out after sunset, look toward the west, boom, there's Venus right there. But Mars is getting dim, right? And we have for the month of June, the strawberry moon on June 24th. And on that particular night, the full moon will be only 18 degrees above the horizon, the lowest point. That number sounds familiar. Well, that's the lowest point of the sun for the winter solstice. It's the opposite. And so it's red because it's low. And you're looking through more atmosphere. It's also referred to as the honeymoon, right? Because it's the month of June and July and August, there's lots of weddings going on. And couples go out and they remember seeing the honeymoon on their wedding night, right? And then on the 5th, we have the aphelion with the sun, the earth is going to be away from the sun. Many kids think it would be the other way around. We think it would work closer to the sun. That's why it's so hot, right? Not the case. So the aphelion, the sun will be 94.5 million miles away from the sun. And on July 11th, if you want to circle your calendar book, there's a great opportunity to see Mars and Venus conjunction. It's going to be a very close proximity. And so you'll see Venus going to be really bright. Mars is very dim. But then over there is going to be the beautiful waxing crescent moon. So that should be a real good start, but it's going to be somewhat low. But I think it's a great opportunity. And then maybe somebody here will get a photograph of this for the RCA calendar in 2022. And then the object of the month would be Messier object 92. And those of you who are familiar with this, it's right above the keystone of Hercules. It's a very easy object. Those of you who are just starting out trying to learn about Messier object, this is a great one to try. Once you find M13, while you're there, go to the upper left, you'll see M92. And so it's fairly easy. It's a great one for beginners if you're out starting out with binoculars and the telescope. And so when you look at these clusters, you're looking in the neighborhood of 250,000, 300,000 stars. And so it looks like a bowl of diamonds to a lot of people. And so it's a fun object to look at. And the space station will be visible from June 27th to August 3rd, mainly mornings for the most part. But it's easy to look at, fun to look at, safe to look at. Go to spotthestation.com to get your sighting time from any location around the world. And the great thing, if you have a star party or a party, if you want a real showstopper, tell them about the space station, right? And I want to talk briefly about the Omni Star Party. We're putting some consideration that it's returning. But I did just get off the phone today with Jen from Stewart State Park and Rooster, for that matter, over the past week. They very much want to do this, but they're having what's called the labor shortage. They don't have enough staff, but there's a real problem with the labor shortage. And so we may not be able to do it because they don't have enough staff at the park. So I will may put out any announcement about the Star Party if we do continue, if we choose to do so. We may just end up doing the Percy's meteor shower at Rooster. That's all. Nothing else. But announcement will be made, and I've got a good number of little private Star parties that are happening, especially in the month of August. And I may put out a call, and I may need 1 or 2 volunteers to help me with these private winery Star parties. They're a lot of fun. They really are. But it's gotten bigger and bigger every year. And this summer we have maybe close to a dozen. But it's a fundraiser for the gala for OMSI. Okay. And so here's the list of things that you can go out and take a picture during the month of June and July. There's plenty of opportunities. So make sure you circle July 11th for that close conjunction with Mars and Venus. So with that, stay healthy, everybody, and go out and enjoy the nighttime sky.
Thanks a lot, Jim. That was very informative as usual. Our speaker tonight is Dave Coulter. Dave began his career as a self-taught software developer after receiving a BA in history from Lewis and Clark College in 2003. While developing software, he spent his summers as an intern at NASA and earned a BS in physics from Portland State in 2015. Turns out he was also a club member in 2009. In 2016, he began his graduate studies in the Astronomy and Astrophysics Department at the University of California, Santa Cruz. In his first year as a graduate student, he received a prestigious National Science Foundation Graduate Research Fellowship. Then in 2017, he was an important member of the team that located the source of a gravitational wave signal in visible light, and was the first author on a paper in the journal Science describing the discovery and the techniques they used to make it. Science featured his paper on its cover and honored the discovery as the 2017 Breakthrough of the Year. Please give a warm and telepathic welcome, and welcome back to Dave Coulter.
Thank you so much for the introduction. Can you hear me all right?
Yeah, we
Good.
got you. We got you.
Good. So can I just go ahead then and share my screen?
Yes.
Great. All right. Ooh, let's see. Oh. Is this still working?
So yes, we see your presentation, but it's not full screen.
Okay. Let me go ahead and, you can hear me all right though, right?
Yeah,
Okay, great.
there you go.
Good. So we're good. We're good. Okay. Yes. Thanks again for the invite to speak here. It's quite a treat to come back. And you know, back when I was going back to school for physics, I joined the Rose City Astronomers in 2009. So this is kind of a nice coming back and updating everyone with my, you know, what I've been up to. So with that, I'll just go ahead and jump right into the talk. And I like to start the talk with this picture of the night sky, because this is really the state of the art in astronomical observing. For thousands of years, people looked at the sky and made observations. And as our technology increased and we were able to look at the night sky in colors that were invisible to our eyes, but we remained the same is that we were looking at the universe in light, right? So this paradigm shift to look at the universe in more than one fundamental force of nature, right? Light is one of 4 fundamental forces of nature. That door was opened by Einstein. So Einstein revolutionized our understanding of light. He also revolutionized our understanding of gravity. To Einstein, gravity is a geometrical effect. Right? It's caused by matter causing space and time to curve. And a consequence of this theory are that gravitational waves should exist. So gravitational waves, they're literal stretching and straining of space and time themselves. They can communicate energy and information just like water waves, although they were a hugely contentious prediction of general relativity in the early 20th century. So it was almost 100 years later when LIGO discovered the first unambiguous signal of gravitational waves from a merging system of black holes. So this is a phenomenal achievement by LIGO. This garnered the Nobel Prize for the discovery, as well as, it was incredible for the precision of the measurement, right? Just the ability to make this measurement was incredible. And astrophysically, it showed us that there's a population of black holes that are this big. Each black hole is about 30 times the mass of the sun. And so when they merged and generated the signal, it was quite a surprise that these kinds of black holes existed out there. So every time you open up a new window into the universe, you see something new. Now, black holes are black for a reason, right? We don't expect them to generate luminous signals when they merge because they're so massive that no light can escape. However, if you want to see something, a guaranteed show, you can think about two neutron stars. So two neutron stars, they're the massive cores of stars after they undergo supernovae. They're made of stuff as opposed to a black hole that has no surface. And you can see here in this artist's rendition, they merge with each other and then generate these gravitational waves that propagate at the speed of light because they're compact and they're massive. But you also see all this associated electromagnetic radiation. So here, as it replays again, you see the gravitational waves being generated. And then when they merge, you'll see a collimated jet or a short gamma ray burst. And so it was thought that these merging neutron stars would produce this pulse of gamma radiation. And then you can see this sort of uniformly expanding blue ejecta that then turns red. So this material is referred to as the kilonova ejecta. And we think that this material actually is a very special site astrophysically. So astrophysically, we think that because of the neutron richness of the ejecta, basically these neutron stars are tearing each other apart, it is the site astrophysically where you can manufacture, you can synthesize very heavy elements very quickly. So elements like gold and platinum and uranium that cannot be created in the centers of stars during their normal lifetimes like the other chemical elements. We think that these things are synthesized in these neutron star mergers. So there are several consequences, though, if you create a large range of radioactive materials like this. For one, there's opacity effects. So essentially, the heavier the element, the more opaque it is. And so I want to connect these electromagnetic signals to what we would consider the observables. And so I heard in the chat someone talking about light curves, and I wanted to kind of contextualize what a light curve is, right? A light curve is a measurement of a brightness over time. And so in the case of light elements, like iron group elements that you would expect from a type 2 supernova, a core collapse supernova, you might expect those light elements to have a relatively lower opacity. And that lower opacity means it's easier for light to escape the ejecta. So if light is faster to escape, that also means that the whole time evolution of that light over time is happening at a much quicker time scale. However, if you have really heavy ejecta, and this is very opaque, it takes a long time for light to get out. And in fact, blue light can't get out at all. So all that light is down scattered into red light to get outside of the ejecta. You would expect that heavy elements would have light curves that would be fainter and redder and slower. And it turns out that by measuring these curves and matching them up to models, we can say, infer what the total amount of ejecta is based on the brightness. We can infer the opacity based on this time scale for the light to change in a given amount of time. And we can also, based on the radioactive decay of those elements, be able to pin sort of like a chemical identity to what must be decaying to power this light curve. And so, like I said, we expect very heavy elements to be produced in this manner, including the gold that's inside of your body. So we think there's about 10 to the 18 atoms, about 0.2 milligrams of gold in every person. And the incredible thing about this, the incredible insight to this, is that that gold was probably generated in a neutron star merger, we think. So here's a new recipe for gold. We can update the alchemists of the of the preceding centuries. What do you need to make gold? You need a few percent of the mass of the sun in neutrons, a dash of iron group elements with which to bombard with those neutrons, as well as the incredible densities and temperatures that you would expect at a neutron star merger. That's how you get gold. And I'd like to invite you to follow me for some more recipes, right? So this is how we build gold, we think, astrophysically. Now, this promise to be able to connect the electromagnetic signals to the gravitational wave signals in order to really prove that these heavy elements are synthesized in these astrophysical sites, we need to find these explosions. And so this is a picture here of a sky map that shows all of the LIGO, what are called localizations in their second observing run. And what I mean by that is there's a gravitational wave event, LIGO detects it, and then they infer the sort of area on the sky where they think it happened. And then me as an observer will go point a telescope and try to search for this. But you can see these regions are enormous, right? They're on the order of hundreds to thousands of square degrees. And if you're looking even with a research class instrument, at least the ones that I have access to, it's like looking through a straw. So how do we find these objects when we have essentially, humongous haystacks? Well, the answer is to burn down the haystack, right? We know that matter in the universe is not uniformly distributed. We know that matter in the universe clumps because of gravity. And so if we are agile in our strategy and we just focus on those galaxies where we think this event will take place, we'll do a lot better for ourselves than rather than mowing the lawn, and just taking sort of tiled images with the telescope. We can hunt and peck for the galaxies that we have algorithms to rank in terms of their probability of hosting this. And so, of course, we have tools in our toolbox here. These are the telescopes that make up the collaboration that discovered this event in 2017. So on the left is the Nickel telescope in San Jose, California, at a observatory called Mount Hamilton Observatory, or Lick Observatory, that's associated with the University of California. And on the right is the Swope telescope in Chile, which I spent many nights at learning how to use and really understanding the nature of like what it means to search for stuff with a telescope. And together, these telescopes, they make up this collaboration called the 1 meter 2 hemispheres telescopes, because they're both 1 meter telescopes. And this has got some obvious advantages. If you have 2 telescopes in 2 hemispheres, you can search all of the sky. And if there's an event that happens where both telescopes can actually point to it, you have redundancy in terms of instrument issues, in terms of weather. So this sets the stage, right? This sets the stage. We know that if we could find electromagnetic counterparts to gravitational waves, we could actually unlock a very deep treasure trove of scientific results. And what I'm particularly interested in are the origin of the heavy elements. We know that we have a strategy now to look for the galaxies as opposed to just looking at empty space. And we have our tools. And so in 2017, I happened to be in Copenhagen, actually, at the Niels Bohr Institute. And back in these days, you had to sign a secrecy agreement with LIGO that if there was an event, you wouldn't talk about it, because they wanted to orchestrate how it was done and published. So sitting in a seminar on gravitational waves, actually, everyone's phones started going off, including mine, with this message, which was a pretty, auspicious moment. And in it, it said that there was a neutron star coalescence at a high degree of confidence. Now, this was game time, right? This is the unicorn that we thought. Not only is it guaranteed to produce an electromagnetic signal, we also thought that it's very close. We have a good shot of looking at it with SWOPE. And not only that, there was an associated gamma ray burst, just like it was predicted from theory. So here is what you'll see on the bottom is the gravitational waveform that LIGO detected. On the top is the Fermi spacecraft that's detecting the short gamma ray burst signal. And I've been assured this is actually what a gamma ray burst sounds like. There it is, right? Incredible. And that crescendo in both frequency space, sort of that high pitch frequency, and also that intensity, that's called the chirp. So that's what a gravitational wave detector will detect. And like I said, not only was this close, not only was it an associated gamma ray burst, but it was a very small localization as well, because the Virgo detector, which is like a sister gravitational wave detector to the LIGO detectors in the United States, in Italy joined the network just in time to be able to essentially shrink these localization regions very small. So what we see here is 30 square degrees. Okay, we can do that with the SWOPE telescope. And in fact, I want to share this text conversation I had with my boss, who had just left for the day to go on a date with his partner. And we had very little actual like internet and phone service. So I'm texting him desperately, like, Ryan, he's my advisor, you need to come back. We need to look for this thing. And he thought this was a joke, right? Not only does he think this is a joke, I'm sitting here trying to convert, my coordinates so that he could see, like, is this even visible? Is this behind the sun, say, right? And I had to really implore him, like, Ryan, please come back. We need to find this thing. And he was convinced. And just to give you a sense of like the timing of why it's so important to get these things as soon as possible, this is a picture of the Earth unrolled, right? And in the black is the night. And in the red is where, it's like an angular separation from the sun. So you can basically interpret this by looking at it and saying, okay, Africa and North America and Europe was pretty much in daytime at the time that GW 170817 was detected. And as time progresses, the Fermi satellite releases their localization information. Then LIGO releases their high confidence, this is a gravitational wave event, people should look for it. But it's not till several hours later that the actual maps that we as astronomers need to go look for this thing are published. And you can see right now there's a telescope, an observatory called the WISE Observatory in Israel, as well as the South African Astronomical Observatory. They may have had a shot potentially to search for this, but the tolerances were very quick, because this region of the sky where LIGO said that the event happened was actually setting, right? So we had to wait basically until the night sky caught up with Chile before we could look. And so we did that with the SWOPE telescope only, because this happened to be in the south. Now in those hours between LVC discovering a gravitational wave counterpart and us actually being on sky and looking was one of the most intense 10 hours of my life, of essentially like running different algorithms to try to prioritize galaxies. And then what we also did, which I think was quite novel compared to other teams at the time, what you're seeing here is the localization region, right? On the horizontal axis is the right ascension, on the vertical axis is the declination, or sort of like the latitude. And the circles represent, or I should say the oval here represents the confidence region that LIGO says that, okay, we think the event is in this space. What I'm going to play for you is like the sequence of events, the sequence of images that we took. So the first image we took at 8:14, 8:17, and you notice that the galaxies clump, right? Because the universe is clumpy. And so besides just ranking these galaxies according to their attributes in terms of how bright they are and their centrality to the probability region here, we were also trying to pack these galaxies together to make our imaging more efficient. And you can see on the 9th image is when we actually imaged the transient. So this is important because we were only 15 minutes ahead of the next major research group, right? So this amount of speed that we were able to bring based on our sort of thinking of the problem also allowed us to take the only spectra of this event within 24 hours, right? Because by the time this was widely circulated and everyone wanted to slew to that position, it had set. So I like to share this Slack conversation that I had with Charlie Kilpatrick, who was a postdoc that I was mentoring under at the time. Charlie, there's a lot of high dollar analysis teams out there that have like machine learning algorithms and all kinds of automatic data reduction. What Charlie did is he was downloading images from DECam from their archive and just blinking them with his eyes. So he's the first human being to say, I think I see something. I think I see optical photons from a gravitational wave source. And here you can see him comparing, above is the template image, and here is the science image. And the feeling of this, of the pause when we're waiting for Charlie to upload that, I think the best image I have to describe that feeling is an image of my daughter. Right when, this also corresponds to me telling my daughter how I was messing up the coordinates, and she just couldn't believe it. So this was the feeling, I think, and this is the image. This is the first image, and the location of the counterpart. Actually, when you become a professional astronomer, you learn these tricks of the trade. during the data reduction step, you get to see this awesome red arrow that points out the new object, right? So this is the first image of an optical counterpart to a gravitational wave source. And when we compare this to imaging taken just months earlier by the Hubble Space Telescope, we can see there was nothing there, right? So this is good indication that it's something new and it's something unique. So, now that we've found this, what can we say, right? What can we say about the origin of the heavy elements? And for that, I am showing you this image. This was the discovery image as well, just taken it as a 3-color image. And you can see the location in the upper left is that blue dot. Okay, just 4 days later, that dot had rapidly faded and become red. So whatever's happening here is happening very, very quickly. And it's happening so quickly that we can't explain it as any other type of transient that we've seen. Supernovae, they take too much longer to evolve rather than this kind of event, which evolved within the course of days, right? And in fact, when we compare this to simulations based in theory, there's remarkable agreement. So what you're seeing on the left-hand side, the dots are actual data taken by the event, by astronomers around the world. And in the solid lines, those are the models that are based on, the very complicated radiative transfer codes that are actually calculating the opacities and the expansion velocities. And what I really want to draw your eyes to is the remarkable agreement between the theory and the observations, because no one had ever seen something like this before. And so to be able to make this very comprehensive and pretty accurate match between the models and the data meant that we could invert those models and then calculate, how much ejecta mass came out of it and at what opacity was that mass, right? And that's what actually let us get to the question, or the answer to the question, of how much heavy elements were produced in this particular merger. So then the question is, how much gold was produced? And it turns out that there was about a Jupiter mass of gold. So yeah, if you could get in a spaceship and fly to NGC 4993 and scoop up that gold, you'd be very rich indeed, although it would be very hot and very ionized and radioactive. So yeah, it produced an amazing amount of gold. And then also we get to look at this story now of how we explain where these elements come from. And we can see now that the lanthanides and the actinides, the part of the periodic table that really pops out, we can definitively say now that some of these elements actually do come from binary neutron star mergers, right? And so it feels like a tremendous privilege to be associated with this decades-long, search that humanity's had for finding these elements. So one top-line conclusion is binary neutron star mergers are important astrophysical sites of the R process. And R process there is just referring to the style of how these elements are built. R stands for rapid, so that's referring to the neutrons, right? Neutron stars are rich in those. And really, locating this to the galaxy tells you a lot more than just, what elements were created. In fact, there was a whole slew of almost 1,000 papers that came out of this from all across the field. And important quantities like making H0 measurement, measuring the local expansion rate of the universe, measuring the speed of gravity, right, by measuring the timing delay between the gravitational wave signal and the gamma ray pulse, and as well as understanding, the galactic neighborhood that this happened in, and understanding, what kind of formation channel might have led to this event. So as was mentioned before, this whole body of work really, including the localization and the discovery of the gravitational wave signal itself, was discovered, or was given this designation of Breakthrough of the Year. So obviously this can't be done by ourselves. We had a fantastic team of very young astronomers, and so you can see basically almost everyone here is a grad student or a postdoc. My advisor and the man directly to his right, Enrico, is the chair of the department. So, but everyone else involved in this was a junior researcher. We all got papers out of it, which is something that you can't really say in a lot of other places. So I feel very thankful to be a part of the team here at Santa Cruz. So with that, I want to kind of wrap it up and thank the Rose City astronomers for hosting me. And I'd love to take questions. I have a lot of additional slides depending on where questions might go. So I'd like to give it back to Mark, and thank you for your attention.
Thanks, Dave. That was great. So the way we've been handling questions is we've been asking people to type them into the chat,
Mhm.
and then either you can read them yourself or I can read them for you. And
I don't think I have the chat like controls up when I'm sharing my screen, so I can stop
Okay.
sharing my screen, or you can read the questions.
I would be very happy to read them.
Okay.
So first I'm going to sneak in, I almost never get a chance to do this, so I'm going to sneak in one question of my own. I'm curious, were there any big theoretical surprises that came
Yes.
out of?
Yeah, no, that's a great question. One of the biggest theory surprises that came out of this was the nature, like really trying to understand the nature of the blue component of this kilonova, right? So if I can maybe show, I'll show you this plot here. This is let me just contextualize this. This is a nuclear reaction network animation. And on the vertical axis, we have the number of protons. And we know that the number of protons in an element correspond to like what type of element it is, right? So hydrogen has 1 proton, helium has 2 protons. And on the horizontal axis, we have the number of neutrons. So for any given element, you can have different configurations of neutrons for different isotopes. When I play this animation forward, what you're seeing essentially are the neutrons being added to the material, which pushes it really far to the right. And then, of course, these become very radioactively unstable. They decay, transmuting those neutrons into protons, and they kind of collapse into this valley of stability. So this process of building up heavy elements with bombarding them with neutrons, this is called the R process. And we expect this stuff to be very opaque, right? And the reason why is because when you have these very complicated elements, they have very complicated valence electron shells. So basically states where the electrons can be. And so if that's the case, where's the blue light coming from, right? And the current thought is that when these neutron stars merged, they were spinning so fast, like their total mass was actually above the critical mass where a neutron star will just collapse into a black hole, right? So that mass is called the TOV mass, the Tolman Oppenheimer Volkoff mass. So it's something like 1.2 solar masses or something like, oh, I'm sorry, 2.1 solar masses, something like that, right? So the total system mass here was above that. And so they think that it was spinning so fastly, or that the centripetal acceleration kind of kept it from collapsing. And in the process of that hypermassive neutron star that was being spin stabilized for a very short amount of time, it was essentially dumping a lot of neutrinos into the material. And those neutrinos essentially converted neutrons into protons. And by doing that, you create this lower opacity material because you don't get to manufacture heavy elements. So, I mean, that's a great question, but I think one of the most interesting questions looking forward is what causes the blue component of these neutron star mergers, and then also what does that say about the potential diversity that we would see in kilonovae. And then remember, if there's a diversity in the kilonovae, there should also be a sort of diversity in the channels for these R process materials to be synthesized.
Thanks. So is the R process experimentally accessible on Earth, or is it something
No.
we only see?
Yeah.
So not even on a tiny scale, we can't.
No. So basically, what it requires is just fluxes, incredibly high fluxes that can only be achieved when you have like explosive decomposition of neutron star material. So those kinds of densities of neutrons, as well as the temperatures, like something around 1 billion Kelvin. So that's just not something that we'll be able to achieve. And actually, historically, when people were first putting together abundance charts and they were trying to understand like, what are the relative abundances of elements on the Earth, right? You can take core samples of the Earth, you can try to separate the elements and calculate what the relative fraction of this element is to that element and try to tie it to natural phenomenon. Where these heavy elements could be was such a challenging question that instead of answering the question of where they came from, scientists actually posed a different question. what kinds of neutron fluxes, what kinds of energies would be required to make this material given our understanding of nuclear physics. And so those extreme values of pressure and density and temperature actually led in the 70s during numerical studies of general relativity, people to say, hey, maybe this comes from a neutron star merger, right? So sort of explaining something so extraordinary required a very extraordinary explanation.
Wow. Wow, great. Thanks. So Rob asks, what's a kilonova?
A kilonova is the name for the actual explosion that you see in optical light and as well as in the infrared light. So when these two objects merge, these neutron stars merge, they can sometimes launch. You see this big collimated jet, that would be the short gamma ray burst. But then the material of expanding ejecta that you see there, right? It starts blue and then it turns red and it kind of looks uniform in its expansion. That's the kilonova. So the kilonova is a luminous transient that's powered by the radioactive decay of the elements synthesized in the merger. So like a supernova, like a thermonuclear supernova, if you have a white dwarf that explodes like a type 1a supernova, that's explosive burning of carbon and oxygen. So this is like explosive burning kind of heavier elements or by the R process.
Very cool. So Mark is wondering, he says, when you found what you thought was the source, he's wondering if you kept taking images just in case you hadn't found the actual source.
Yes, we definitely did that. And I think you can see from this slide here that we were also actually searching with other telescopes as well. And so, you know, when we got that source and we said, okay, there's something there, we didn't want to tell the rest of the astronomical community to stop looking, right? In case we were wrong, in case the thing that we were looking at might have been an asteroid or it might have been a pre-existing supernova. So we did continue our search protocol with all our telescopes until we were able to do those cross checks to see, is this an existing object that people know about? And only after we were able to be reasonably sure that it was probably the supernova. I think I have here. This was the circular that we sent out, that I sent out, saying that this is probably associated with the gravitational wave event. So yeah, so we were still searching. We took many images, and you know, once we were reasonably sure, we sort of alerted the rest of the community.
Thanks. Holly was wondering when you first became interested in astronomy or the night sky.
I think that I've always been curious about it. When I went to college the first time, right, in 1999, I had dreams of being a double major in physics and math, and I didn't have the academic preparation for it. So I ended up switching tacks and sort of focusing on history and political science. But it always was stuck in the back of my head that I wanted to study outer space, you know. And like I was mentioning at the beginning of the meeting here, it really was, you know, getting a job as a software engineer kind of gave me the resources to go back to school. And, you know, joining this group here has really ignited my passion for it as well, to see things through telescopes. And that's actually what made me be an observer as opposed to a theorist, you know, the sort of romance of being able to go out to the sky and see stuff that was real, not just theorized. And so I think we're in a lucky time, actually, in this particular science that I'm a part of, in that there are a lot of theories. There are a lot of theories for what generate the blue component. There's a lot of theories for how and whether and what kinds of materials are synthesized in the explosions. And it's really up to observers to make the measurements. And by doing that, be able to sort of rule out parts of parameter space, right, that may not agree with the observations. So I kind of feel like we're in an observation forward phase where before LIGO turned on, before LIGO was able to locate these things where astronomers could then point their telescopes, really it was the theorists leading the way, trying to understand, what these would look like gravitationally, what they would look like electromagnetically.
So Mike is wondering if there's anything else you can do besides having more gravitational wave observatories to shrink the uncertainty regions on the sky.
No, not really. Let's see if I have another good slide for that. It would be, sorry, I'm just looking for this slide. I think that would answer that question straight away. Well, I don't have it offhand, so I'm going to go ahead and defer just to the explanation here. But the way that LIGO works is it works by timing delays. So there's sort of a time of flight of the gravitational wave when it hits one detector, and then separated on the Earth, it hits another detector. And so it's the timing delay between the detectors that allows them to triangulate the position on the sky. So it's sort of a convolution of the antenna sensitivity pattern, because you have to take into account the detector sensitivity as well. So it's the timing delays between these. And so the more detectors you have in the network, essentially the more those error regions can be constrained. But the good news is that there are a lot more detectors coming online. And not only that, the detectors that are coming online are becoming more sensitive. So you've got LIGO in Washington and Louisiana. You have Virgo that's also joined the network, and at the end of the second observing run that's got a boost. You've got Kagra in Japan, and then LIGO India, which will be in the 2030s. And so all of these are projected to actually shrink those error regions to sub 10-degree regions, right? And these things could also be bright enough where amateurs could find them as well. So actually, one of my other efforts in grad school is building software tools to allow anybody who can define their field of view of their telescope and their geographic position to sort of search as well as the pros with the big instruments, right? Because as we saw for the kilonova in 2017, it really was about sort of picking the right galaxies to look at, and it was really timing based, right? If someone had seen or had been able to execute their search program in Africa, they could have seen it almost 10 hours prior to when we saw it in Chile. So I think the future is bright for people to join in the search and be able to contribute, especially with smaller areas.
Do you know Frank Marchis? He's at SETI. And
I don't personally, yeah.
So he's been creating this, he has the small telescope called the EV scope that he's been selling, promoting. And the idea is basically to have amateurs gather a lot of scientifically useful information. And it all kind of gets funneled into, I don't know if the scope would be sensitive enough or, big enough to contribute in that regard, but he might be somebody you might want to talk to sometime.
It really depends on the proximity. So like for this event that happened in 2017, it was relatively next door. It was 40 megaparsecs away.
Yeah.
So that's a pretty close by galaxy. You get into this situation where LIGO gets more and more sensitive, and then it's pushing the range at which it can see these neutron star mergers further and further. And of course, as you go further away for a given brightness, it's going to look dimmer. So it's even challenging for for professional astronomers, especially if these things are at like 100 megaparsecs or 150 megaparsecs. And that's where we think the median detections will be in the next observing run. So starting in June 2022, LIGO should be doing its fourth observing run with improved sensitivities. And our team actually at Santa Cruz has got a Cycle 1 JWST, James Webb Space Telescope, proposal accepted. And so there's a big chain of ifs, but if it launches and doesn't explode, and if LIGO turns on, and if there is a discovered kilonova in 04, then we will trigger our JWST proposal, which means that we will have these really spectacular data in the infrared, right where you would expect these transients to be the most interesting, where you might be able to actually get chemical fingerprints of what was synthesized in those explosions. And I'm actually set up to have a leadership role in writing those analyses. So really looking forward to 2022 and beyond, both to get these smaller error regions where we can find maybe more stuff, but also to be able to trigger some of the big guns that we have to get at some of the deeper science.
Yeah, that's really exciting. So Daryl asks a related question. He's wondering what the likelihood of a neutron star merger is.
Well, that's a good question. It really sort of depends on the detailed physics of how the binary system itself is created, right? And so from the gravitational waves, we know that the time to merger goes something like the separation between the two objects to the fourth power. And I know it's mathy, but what it's saying is that if things are really far away, it'll take much longer than the age of the universe for the gravitational waves to be efficient at tightening up the orbit. And if you get things that are very close, they can merge within the age of the universe. And so there's an active question in the field, which is like, how do you build binary systems that are that tightly joined? And so there's lots of different explanations you could have, what are called common envelope episodes, where one star goes a supernova and becomes a neutron star, and then the other star starts to evolve where its envelope gets larger, and then you sort of have this envelope that is common to both cores, basically both pieces of like what will eventually become neutron stars, and then that drives the binary closer together. So but as far as like what LIGO can measure what its sensitivity is in a volumetric sense, right? It knows like generally how far away it's sensitive to, and it knows generally the area on the sky it's sensitive to. So LIGO can calculate a volume, and then LIGO knows how long it was running, so then it can calculate a rate. And so for neutron star mergers, it's something around 500, a few hundred per year per gigaparsec, and gigaparsec is an awfully large volume of space. But I think it translates into, oh, I don't want to get this wrong. I should know this off the top of my head, but it translates into something like 1 every century per Milky Way galaxy, something like that. I'll get back to you if I said that wrong. But basically, yeah, we would expect to see. So, you know, putting that rate into perspective with the next run of LIGO, we'd expect maybe 10 neutron star mergers to happen in a year-long run of LIGO 04. Now, maybe not all of them will be visible because some might be behind the sun or some might not be localized, but we think maybe one would have the magic number of attributes to be able to be visible by the James Webb Space Telescope.
Cool, excellent. So Mark is wondering what the source of neutrinos is in a neutron star merger. He says it's all neutrons and no leptons. So where do you get the lepton numbers to produce neutrinos?
So the neutrinos are produced by the extreme temperatures. So really hot reactions or really hot things can actually cool themselves off by generating neutrinos. And so these neutrinos, so this is a great question. I didn't really go into too much depth about this, but when there's a kilonova explosion, let me go back to that animation, which is pretty neat. Actually, I might have a better picture. Let's see. Here we go. So this is a schematic of a neutron star merger. And you can see that there are like different physical processes at play. You can see sort of the vertically collimated thing being the gamma ray burst. However, if you have a neutron star merger where the remnant is itself a very, very hot, rapidly rotating neutron star, that will just cool itself in the form of neutrinos. And in fact, like during a core collapse supernova, when a neutron star is formed from the beginning, you have all this material collapsing to supranuclear densities, and then it bounces, and that bounce back actually launches the envelope of the massive star and creates the supernova. The radiative energy, the power of that supernova is actually almost all in neutrinos. So it's like 10 to the 53 ergs, 10 to the 53 power of anything is a lot. So basically a huge amount of that energy is released as neutrinos. About 1/100th of that energy is in the kinetic energy, and about 100th of the kinetic energy is in the luminous energy. So really, these kinds of explosions and collisions are actually much brighter in neutrinos than they are in electromagnetic radiation. It's just that neutrinos don't interact with matter very much. Like a neutrino can go through a light year lead and not interact. So then, going back to this question, if you have these neutron stars that merge and then they create this sort of, short-lived remnant, that itself can be hot enough to just generate neutrinos and kind of act like a neutrino light bulb. And then those neutrinos can interact with free neutrons and turn them into protons. Now, the other side of looking at this is if you have a merger between a neutron star and a black hole, that will never produce a neutron star remnant. They'll always produce a black hole remnant. Or if you have two neutron stars that are very massive, that they're very much above that threshold neutron star mass, they will produce a black hole as well, right? A prompt collapse. And that essentially shuts off a source of neutrinos. And by shutting off that source of neutrinos, you also encourage heavier elements to be synthesized because those neutrons are not being changed into protons. And therefore you get that sort of that R process plot that I showed where it kind of builds up rapidly. So this is another question that's related to the kilonova diversity. If depending on the colors and the time evolution of these objects, we can infer, what was left over. We can infer the remnant mass, or not the remnant mass, the remnant nature. Right? The gravitational waves can tell us how massive it is, but it can't tell us if it is a neutron star or a black hole. So it's only looking at the light and seeing the associated color changes will tell us, what the nature of the remnant is. And so the neutrinos, really, they're coming from the cooling of this very hot, dense matter, and they change the nucleosynthesis.
Okay, cool. So Jim's wondering what you're envisioning is next in your career.
Next in my career is hopefully to get a postdoc at a well-resourced institution. Well-resourced is what I mean is like they have telescopes and we can go hunt for these things, right? So I'd love to go to Carnegie. I'd love to go to Space Telescope in Maryland, but anywhere where we can keep pushing the boundaries and keep finding new and interesting and exploding exotica, right? With fast time domain surveys is an exciting place for me. So I'd like to do that next.
And he's also wondering maybe 10 years from now, what you're envisioning you might be doing.
Oh, geez, man, given the state of the world and COVID and all these crazy things happening, maybe I'll be a shipwright. I don't know. But I think that, I'd love to be at an institution. I'd love to be, I think, I've had this boyhood dream of working at NASA just because that's, I've spent some time there and had a great time at NASA Goddard. So that's what I'd like to do. I'd like to do this professionally if I could.
So let's see. So Howard is wondering how large the masses of the progenitor neutron stars would have to be for them to result in a black hole. And if that occurs, would they still produce the heavy elements?
So I think are you asking like how heavy can a neutron star be before it collapses into a black hole?
I think he was wondering how large they could be in the merger, how large they would need to be in the merger to form a black hole at the end. And if they did form a black hole, would they still produce the elements, the heavy elements?
Yeah, so I mean that's a great question. That's related to this TOV mass, this Tolman-Oppenheimer-Volkoff mass, and so that's related to something called the neutron star equation of state, which basically says like how dense can things get, before they just collapse. And so from this event, from GW 170817, we think that mass is somewhere around 2.1, 2.2 solar masses. So that's as large as the remnant can be and still possibly be a neutron star. Once you get above that, it's going to collapse to a black hole. Now the question is how, is there something else there that kind of keeps it afloat for a second? So if these were non-spinning cold black hole or cold neutron stars, right, they would just collapse into a black hole if they exceeded that mass. if they did exceed that mass, but they're very hot, so they're kind of a little bit more puffy because they're hot, or if they were spinning very quickly, they could momentarily exceed that maximum neutron star mass. So but it's absolutely true that if something promptly collapsed to a black hole, there would be no neutrinos, and if there's no neutrinos, you would produce more heavy elements actually, versus if you had you know, a delayed collapse, or maybe you formed a neutron star in the remnant that was light enough to remain a neutron star, you would form very little heavy elements by comparison. Essentially, those neutrons would be, you know, turned into protons.
Thanks. Steve is wondering if your discovery of the visible source helped improve the accuracy of future LIGO gravitational wave measurements.
Well, it certainly helped improve a lot of the gravitationally like derived parameters of the system. So here's a fun equation that I can show. Now that we're all friends, we can look at equations. So here, the quantities that a gravitational wave detector actually measure really are the strain. So this is the bottom equation that starts with an H. That's the strain amplitude, or like the degree to which the gravitational waves like change the length of the detector arms. And the F's are the frequency of the gravitational wave response. And the F with a dot on it is like the rate of change of that. So by measuring the strain amplitude changes and measuring the frequency response of the detector, you can understand like the quantities like mass and distance to the event. But it's also true that if the event is edge on, it'll essentially be quieter than if it's face on, right? So there's an inclination angle effect where if they're inclined to face us, they could either be larger systems or, you know, or smaller systems that are closer to us. And so because of that, there's an uncertainty in the gravitational wave information. So that luminosity distance that you can measure from the gravitational waves is itself a little bit uncertain because it's sort of degenerate with like the inclination angle of the system. So measuring an optical counterpart gives you an independent measurement of the distance to that object, which can help constrain the inclination of the system. Also for GW 170817, there was a gamma ray burst, but like my advisor said in that chat, you know, he's like the X-ray should be booming from this gravitational, you know, from this GRB that's pointed at us, but it turned out that it wasn't pointed at us. It was pointed like 20 degrees away from us. And so being able to see that electromagnetically gives you a constraint independently on the inclination angle of the system. And so that tightens everything up. So once you can find it, you can get an independent redshift, you can get a independent distance measurement, and you can get an independent constraint on the inclination angle. So I would say that finding electromagnetic counterparts basically reduces a lot of the uncertainties in the gravitational waveform.
Yeah, that's great. Jeff is envisioning a situation where we could use all 4 fundamental forces to image events. And he was wondering if the neutrinos, I think he's asking if you would be able to see the neutrinos if you could image with the strong or weak nuclear force.
Well,
No,
so
that's not the question.
Okay, go ahead, Jeff.
The
Ask
question
away.
is, would the neutrinos correspond to a weak or a strong nuclear force
a week.
as a mode? Okay.
Yeah,
thank you.
yeah. And actually, the first multi-messenger detection actually was of neutrinos and light. So instead of gravity waves or gravitational waves, it was neutrinos and it was light. And it was from supernova 1987A. So supernova 1987A happened. And then shortly thereafter, neutrino detectors had detected about 20 high energy neutrinos that they traced back to the actual event. So they had direct contact sort of to like the nuclear reactions that happened at the core of that star. So, but neutrinos, you know, they're very hard to detect, right? Because I mentioned before that they could go through a lot of material without interacting. And so to to basically find neutrinos, you have to have these very large detectors that have a lot of sort of cross section for the neutrinos to interact with. So you have, like in Antarctica, Ice Cube, which is this giant detector that basically uses a giant block of glacial ice. And if the neutrino interacts with that ice at all, it might produce a cascade of particles that then can be detected. So, so definitely neutrinos are going to be a part of moving forward with this multi-messenger astronomy, because you'd love to see neutrinos, light, and gravitational waves. I would tell you the neutrinos, because they trace the weak force, will tell you about the nuclear reactions that are happening inside the the merger or the explosion, which can also tell you about the nucleosynthesis directly. And the gravitational waves will tell you things about, like the system, the masses, the spins, the inclinations, the distance. And then the light tells you about composition and about the amount of ejecta and its opacity. So that's the promise, is being able to combine all of these things together.
So Margaret's very impressed with how well you're doing as a history major.
Right. Well, I do think that that the liberal arts education certainly helped. You know, there's a lot of public speaking involved in science, which I didn't really appreciate before I got into it. And you know, just understanding what we do in the larger historical thrust of just, you know, what, you know, being in a place like Copenhagen and appreciating the quantum revolution happening there, and then being a part of like this gravitational wave astronomy revolution in a place like that, like just appreciating that history and the narratives there has, I think, definitely enhanced my view of all this.
So Mark is wondering if neutrinos have been detected from any other kilonovas.
Not that we know of. Yeah, there have been, however, efforts to detect kilonovae without gravitational waves, right? And so one way that people try to do that is they look for short gamma ray bursts, right? These gamma ray bursts that we now know are associated with neutron star mergers. And there are satellites like the SWIFT satellite that can rapidly slew to the position of where a gamma ray burst happens and measure the afterglow. And when measuring that gamma ray burst afterglow, they look for excesses of light in the infrared. And by finding excesses of light in the infrared, they can try to say pin down like maybe what the total amount of radioactive material that could have been produced. So especially with these very fast time domain surveys that are coming online soon, like the LSST or the large, it's now called the Vera Rubin Observatory, right? So this will be taking large swaths of the sky and image it very quickly, you know, day after day. And so because of these high cadences, you might be able to see very rapidly evolving transients that you would miss in other surveys. So there will be untargeted kilonovae surveys that are looking for these kinds of events or signatures of these events, either through this sort of very rapid survey of time and space, or by trying to look for excesses in the light curves of short gamma ray burst afterglows.
Of course, that's if you can process the data quickly enough from the Vera Rubin.
Yeah, that's right. And that's a huge other data science thing that's going on with all of the you know, the artificial intelligence and machine learning to try to you know, pattern match, really, because there's no way even all of the humans on Earth could search all those images. We don't have enough Charlies to blink the templates of the science images to be able to find those things.
So Edward's wondering about the different roles of the theoreticians and the experimentalists in this whole process. Could you say something about that? Yeah,
it's really hand in glove. Like a lot of the theorists that are the sort of the most preeminent right now with at least the electromagnetic, you know, phenomenology, like what do we expect it to look like, and how can we invert those models to find out how much stuff was made. There's really a couple really important scientists. There's Dan Kaysen, who's at UC Berkeley, and then there's Brian Metzger, who's at Columbia. And there's a lot more too. I'm just focusing on those two because those two had these very detailed models that sort of decomposed the light that we would see into those quantities of interest. And so, like I was showing with the let's see, with the predictions of theory, sorry, here we go. There we go. So like I was showing in this video here, you know, the predictions of theory were so, you know, relatively spot on for something that no one had ever seen before. So there's definitely a lot of work that theorists do to set up the observers to be able to interpret their results. And this is just, you know, this is just one aspect of it, because there are numerical GR people that are actually doing the very complicated, like gravitational like math to see how space-time is churning when these things are merging, and then they give those results to other people that then do the neutrino transport, like how do neutrinos diffuse through this material that's moving relativistically, and then that gets given to other theorists that do like nuclear reaction networks that say, okay, well, given the state of the background of the energy in the neutrinos, you know, what kind of elements are created, and then you have people like Dan Kaysen's group that are actually running like opacity models. Right, so there's a huge amount of theory that goes into like, you know, trying to come up with realistic models for what this stuff looks like. In a way, I got the easy job. I just point a telescope and see if I can find something. But yeah, theory really does heavily impact what we do. But like I said, now we're in the place where there's a lot of theory, and there's no shortage of theory actually. So it's really going to, the insights are going to be driven by the discoveries. And the discoveries are super time sensitive. So this is going to be like a Wild West, which is part of the reason why I wanted to call the talk, you know, the multi-messenger gold rush, because I think it really is. I think this is the time when everybody is trying to stake their claim and trying to find the next kilonova. And I just, you know, I'm just pleased to be involved, you know, so.
So Jeff had a follow-up to his earlier question, and he was wondering what the carrier or what the messenger would be that would be associated with the strong nuclear force.
Yeah, that's, I mean, the force particle for a strong force is the gluon, right? And they have ultra short ranges. So I would think that you'd have to detect the strong force, you know, like by inference. And you know, I'm not quite sure what it would be. I've had the same question. Maybe it's you're talking about distance scales that are like on the scale of nuclei. So any signal that comes out of an astronomical event that depends on distance scales, the size of nuclei, like maybe cosmic rays, you know, those are protons being accelerated by supernova remnants and things like that. Those might, you might plausibly say that they trace the strong force in some ways, but yeah, the real answer to your question is I'm not quite sure what the observable would be for what I do.
The gluons make pions, which decay
Right.
to muons, so you get a muon burst maybe.
Right, but
And
muons
cosmic rays.
themselves have a lifespan, right? So yeah, I mean, you might be able to see something like that. So it would be a particle detector then. It would be another particle, like a Cherenkov detector maybe. Like they have in the mountains of Mexico, they've got these big water tanks that are looking for basically particle scatterings.
So at this point, we've kind of reached the end of our questions, and coincidentally, we're right about at 9 o'clock. So I want to just take a moment and thank Dave again. It was really great to hear about your work. It's very exciting. And
yeah, thank you very much for having me. It's been a lot of fun.
And Dave, I don't know if you're willing, if anybody else has any additional questions, maybe Dave would be willing to stick around for a few more minutes. I don't know.
Sure.
Okay. But as far as the formal meeting goes, I think we'll go ahead and we'll end it. So for anyone who doesn't want to stick around, please feel free to leave as you like. Thank you very much for coming, and hope to see you again next meeting. And you're getting a lot of appreciation in the chat right now, Dave.
Oh, great. Thanks. As a grad student, you need it, you know, you love to see it.
Yeah. But it was great to hear that you got through that most recent milestone.
Right. Yeah. So for
It's
people that
enormous.
don't know, I just qualified. So that's a portion of your PhD where you sort of have to go through this oral defense and cross-examination and answer lots of questions. So this is the secondary oral exam for me. So you know, but that's good. It means the next thing between me and defending my thesis and graduating is the few papers that I have outlined that I'd like to accomplish.
Yep, lots of appreciation. I'm just seeing, just kind of scrolling through more. So if anybody has any additional questions, please put them in the chat. Or in fact, since we're a smaller group now, feel free to unmute and you can even turn on your camera as you like and ask Dave directly.
Hey, Rob Brown here. I asked a question earlier and I'm going to follow it up. Why kilonova and not meganova or millinova? What's special about kilo?
So it's called a kilonova. The way it was coined was actually that it's 1,000 times less powerful than a supernova, but 1,000 times more powerful than a classical nova, which is like an eruption on a white dwarf.
Wow.
So that's where kilonova comes from. And actually, there was sort of like beef between theorists because one theorist called it a macronova and the other theorist called it a kilonova. So it's funny that these terms have been at war with each other, but I think now the generally accepted term is kilonova, which refers to that thousandth factor.
Thank you. It's wonderful to hear that it actually means something, that it's
Yeah.
right in between the
Yeah.
two that we're most familiar with.
Right,
That's
right.
cool.
So yeah, and it's interesting that it just happens to be that way too, right? Like order of
Yeah.
magnitude. So
Yeah, very good.
I thought I saw some reports or papers somewhere about other kilonovas being observed or suspected kilonovas, but you implied in your response to my earlier question that no other kilonovas have been for sure observed, I guess. Are there any
Yeah.
suspects or?
Yeah, there have been, like I mentioned, those studies that look for excesses in the light curves of other phenomenon like short gamma ray bursts. There have been identifications of kilonova-like signals, and then if you assume it's a kilonova, then you can back out like what the mass synthesized is. And so there has not been like another bulletproof sort of kilonova discovered and widely agreed upon to be a kilonova. There have been one or two transients, at least one that has seen to be kilonova-like if you make certain assumptions.
But nothing has matched up exactly with the clear signature we saw with the gravitational wave counterpart.
Right. So the gravitational wave counterpart was really what sealed the deal, because you can also run the sort of statistics and say like, okay, the localization was 30 square degrees. It was really small localization. And LIGO at that time didn't have that far of a range, right? So you're looking at actually a really small volume of space where this could have happened in. And when you look at the rate of other kinds of transients, like the rate of supernovae or the rate of asteroids, the rate of whatever, right? And you calculate that volumetric rate times the volume that LIGO is sensitive to, you find that it's like a 1 in a million shot for the thing that we detected as a kilonova to be something else, like a chance coincidence with a supernova, say. So it's harder to do that when you don't have that volume constraint from LIGO.
So these aren't actually very bright. I mean, like the blue magnitude at what was the distance of this one?
40 megaparsecs, which is a distance
so about 100
modulus
million,
of, yeah, it's like
100
30
million light years. Yeah.
So to put it in absolute magnitude terms, because I've heard you guys talk about absolute magnitudes, it's like it peaks at -16.
Right,
We're at-
but in terms of astronomical magnitude, not absolute magnitude. I mean, that's,
Well,
yeah, I
so
mean,
so
that's,
you to
yeah,
get the apparent magnitude, you just
yeah,
add the
apparent.
distance modulus to the absolute
Oh,
magnitude.
yeah, okay, so minus 16, okay, just
Yeah,
work it
so
out from there. So
minus
about
16.
minus 16 versus like minus 21 for a typical spiral galaxy or something like that.
Yeah. So it would have been like 20th magnitude, something like that.
Wow, at 100 million light years. Wow, that's dim.
Yeah, so it's a lot dimmer than a supernova, right? A supernova, like a
Right.
type 1a supernova, will peak at minus 19. So that'd be 3 magnitudes
Oh,
brighter, right? So
wow, okay.
18th magnitude, yeah, quite a bit different.
Yeah. Yeah, that's a pretty deep image. Okay. All right. Yeah, interesting.
So do people feel like they're actually localizing the neutrino signals? 'Cause it seems
No,
like it
no,
seems
I
like
mean,
there's
like,
only a handful of detections, or maybe
yeah,
even one or two.
yeah. I mean, and also to get a neutrino from an extra galactic source that's a lot further away than the local group would be a big. I mean, you'd have to just. I don't even can imagine like what the data analysis would be for you to have the confidence to say that neutrino was from
Right.
that event. You'd have to look at both the direction, right? So you see like these particle scatter trails inside the detector to back out like what direction it came from. But you'd also have to look at the spectra of it, right? And the spectra for particles like neutrinos is basically like you've got to infer what the spectra is, right? Like, because
Right.
when you do like particle observations, like if you have an X-ray telescope and you're looking at the X-ray sky, you're not getting like a flux of X-rays. You're getting like individual X-ray photons, and so then
Right.
you have to do like this special Poisson statistics to try to like understand like, okay, what does that say about the underlying real rate that they're being produced? And then you have to sort of infer like a spectral index, like, and what that means really is like what fraction of these photons will be very high energy, and what fraction of these photons will be kind of lower energy. That gives you sort of like astronomers love power laws, but basically
Yeah.
it gives you like a spectra for what you'd expect. And so for neutrinos, it's the same way. So if you wanted to associate a neutrino to something like a kilonova, you'd probably have to have a good understanding of what the spectral index is and the direction it came from, right? The timing difference between that and the gravitational wave. So I would imagine, I don't know much about it, but I would imagine it's a very involved calculation.
But neutrinos were detected from this gravitational wave source. So does that mean that kilonovas
They weren't.
Oh, they weren't. Oh, I thought.
It said it in the circular, but they took that back actually.
Oh, okay.
Yeah.
Okay.
Yeah.
Because that was like, that would imply, but that means that a kilonova would be brighter than a supernova in neutrinos, which doesn't make sense from
Yeah.
what you said.
They didn't. Yeah, they didn't see it.
Okay.
Although that would have been wild if they had.
Yeah.
Yeah.
Do you,
Right.
do you know what the largest number of neutrinos that people think might have been associated with an individual event?
I think it's
What has been?
1987A. I
Oh,
think it's
okay.
like, the 20 or so neutrinos that are associated with that particular supernova.
And do you know
Because
how?
there's also a source of neutrinos right next door, right? The sun is just dumping tons of neutrinos from
Right.
fusion. So I know that neutrino detectors have to separate the solar signal from what might be extragalactic.
And how spread out in time were those 20 some?
I
You
don't know
know?
offhand. Yeah, I hate to say the wrong thing, but I don't know offhand. But I'm pretty sure it'll be right there on Wikipedia.
Yeah.
Yeah.
I think it was under 30 seconds.
Oh, okay.
I mean, it
I
was
mean,
really
they travel
short.
at virtually the speed of light. So yeah.
It just,
But the
neutron
events
star, bang.
themselves last, like supernovae, last for a significant amount of time.
And that's related to that opacity that I was referring to before. So when you have this really hot ejecta, like from a supernova, you have a lot of it. It's also kind of opaque. And so that opacity sets the time scale. It's called the diffusion time for the photons to escape.
Right.
And so there's a couple different forces at play. There's like the expansion of the remnant. And as it expands, it cools. And as it expands, it also gets, thinner. And then you have at some point where the diffusion timescale equals the timescale that the whole thing has been going on. And that's really where you get the peak of the light curve. And then the light curve will start to decline, right? And the photosphere will start to recede into the ejecta, because the outer layers of the ejecta are becoming transparent.
Right.
And then what ends up happening is you have additional sources of power depending on what your supernova is. So if you're a type 1a supernova, you might have the radioactive decay of nickel turning into cobalt, and that cobalt then turning into iron, and that will release gamma rays when it decays, and those gamma rays will then be captured by that ejecta and then thermalized. And so you'll see like the light curve will be powered by that radioactive decay. And if you measure that slope, you can say like, okay, there's this much nickel was synthesized. On the other hand, for like a type 2P, P stands for plateau, the light curve will go down and then the light curve will kind of flatten out for a while. And it flattens out for a while because essentially the hydrogen in the envelope of the star that had been shocked and ionized is recombining. And as the electrons are jumping back onto their protons, it's releasing energy that is then powering the light curve. So depending on the situation, you have different physical processes that are sort of extending that light curve forward in time. For a kilonova, it's we think it's all radioactive material. It's all very heavy, very high opacities, and because like a relatively small amount of material is produced, the overall luminosity is low, and then it dips down, and then you can't see it anymore with like ground-based observatories or even space-based. So then, looking for kilonovae with space-based observatories, you can do it in the radio, or I'm sorry, in the X-ray. Like if you're looking for like years afterwards, years after the kilonova, finally that ejecta might be slamming into, the interstellar medium, and then you might get radio, and you might get X-rays from that. So there will continue to be like essentially electromagnetic counterparts from this event as different pieces of the kilonova are interacting with the environment around it.
But there's probably really only one early burst of neutrinos typically.
Oh yeah, as far as the neutrinos, that'll be right at the beginning. Yeah. Unless you have, like a long-lived neutron star in the center, that's just pumping it out still. But then that, like I said, that'll have a lot of effects on the light curve, including the color, right? Because that color is dependent on the opacity, and that opacity is dependent on the amount of material that's synthesized. So you have more neutrino irradiation, you have less heavy elements. So that'll affect it.
Thanks.
Yeah. No, I do apologize for how brief. I didn't realize that the presentation would be as brief, but then it gave a lot of time for questions. So I tried to do my best there.
No, I think it worked out just fine.
Yeah. Well, any other questions? I'm happy to keep going, or if you guys are ready to call it a meeting, I could let you go.
Yeah.
Yeah, so I'm not seeing any other questions in the chat, and nobody else is unmuted.
Thanks for all the info. It was really good presentation.
Yeah, thanks so much for having me. It's been a real treat.
It was great.
Maybe when we find the next one, I could come back. So
yeah, well, and maybe you can come back in person.
Yeah, that'd be great.
Yeah. Well, nice to see you. Thanks again.
Thank you.
A lot of fun. All the best with the next discovery. It's really exciting.
Yeah. Okay, and stay safe, and thank you very much.
Thanks, you too. Take care. Thanks,
Bye-bye.
everybody. Hopefully see you next month.
Thank you.